to the Australasian Bayesian Network Modelling Society. The purpose of the Society is to promote the understanding and use of Bayesian network models for a broad range of scientific, industrial and research applications. Through the Society, we have created a unique webinar series designed to introduce you to the wonderful world of Bayesian network modelling. You can find out more about the Society and upcoming events, including our annual conference, through our website and social media.
Shannon, and hi everybody. Thanks for all being here. In the last episode, Dr. Sandra Johnson did an outstanding job introducing Bayesian networks. And if you missed that, go to the Society's YouTube page and please enjoy her recording there, but not right now. This episode will explore the nuances and some of the tangled knots of what constitutes the concept of probability. So this will be a brief dip into some key concepts, a bit of philosophical thinking regarding concepts of probability. So let's start with a nudge for you to consider during this talk, and we'll come back to this at the end. What do you think is the greatest question, quandary, or concern about the concept of probability? The greatest question, quandary, or concern? Perhaps you've run into some of this in your own work. We'll come back to this later. Here's what I'll be covering. What's meant by probability, by being probable? Is probability fractal? Is probability absolute? And does probability really even exist? So what's meant by being probable? What's meant by something being probable? For that, let's turn to the etymology of the word probable. It derives from the late 14th century Old French and Latin with a terrible hodgepodge mix of concepts, including believed, likely, pleasing, and even more evidence for than against, suggesting that we cannot speak of low probability events. That can't be right. So let's jump to modern day times. Probability is too often conflated and confused with other terms, and especially my pet peeve, likelihood, which is really a measure of the possible prior causes given some outcome, not the other way around, which is probability. And also it's confused with odds, which is really a ratio of the probability of something happening to it not happening. Probability helps us calculate and helps us inform risk and its many variations of risk exposure, risk frequency, relative risk, residual risk, and so on. These are all just different ways to think about risk, but risk is not quite the same as probability. Too often you hear the term risk when the correct term really should just be probability. And this, I'm finding it often happens with incidents of wildfire, fire risk, risk of fire. Well, it's really meant to be probability, unless you're talking about what is being lost, what the utility is there. And it's where probability really is only one part of a risk assessment framework. So let's continue to be sure to get our terms right. Let's all get on the probability bus. Yes, this is a real bus. Where else in New Zealand, you people, Bayes buses, love it. So now of keen interest to this webinar series is indeed Bayesian statistics, focally Bayesian network modeling, in which Bayesian conditional probability plays a central role. Essentially, as we know, at its very, very simplest, we're interested in how some effect results from some cause, from some causal agent. And we calculate it as the probability of the effect given the cause you observe some cause and predict the effect, the outcome. And this is calculated using Bayes' theorem, which you all probably know. Sorry. And this is used to calculate what we want in the end, the posterior conditional probability of the effect given the cause. And this is calculated using the observed or hypothesized conditional probabilities, the unconditional prior probabilities, and usually some sort of a normalizing factor, such that the answer varies between 0 and 1, and all the probabilities among all the effects add up to 1. Now, it's that unconditional set of priors that can be pretty tricky to parameterize, in part because the resulting probability of effect can be very sensitive to those priors. And are the prior probabilities to be derived from some observed frequency distribution, from some belief, from some model outcome? What are they really meant to represent? The observed conditional probability here as part of the formula is depicted in Bayesian networks in conditional probability tables. So where do these probabilities come from? From real-world outcomes, from expert knowledge, best guesses? And the answer to all this kind of tends to be a mixed, messy yes. So then what does that mean for the final outcome? What does that tend to represent? Does that tend to represent real-world predictions, hypotheses, frequency distributions, outcomes of singular events, outcomes of repeated trials? Again, too often it's at best unclear, or at worst, it's kind of a mixed yes. So it's important that we're really clear as to what we're talking about here. Furthermore, are any of these probabilities the same as the degree of confidence that we would have in their values? Confidence. I would argue that the answer is and should be a hard no. And even the experts can get it wrong, such as the IPCC climate change group confusing confidence with probability, such as in their published crosswalk table shown here. I would argue that confidence should not be equated to probability, at least in the Bayesian context. Confidence is, in a sense, a meta statement about probability. It's not the same as probability. So my overall point here is that each of these elements can be interpreted and defined, just like the etymology itself that we saw, in terribly disparate ways, rendering the overall formulation confusing at best and just illogical and perhaps misleading at worst. These are some of the many faces of probability that we really need to be clear about. Let's take a little side trip here, and let's talk about what I call the fractal nature of causality and probability. What? So we're generally interested in determining an outcome, an effect, which we calculate as the probability of the effect given some cause. But not any cause, a primary cause, a proximate cause. Remember that causal networks, especially Bayesian networks, generally operate as first-order Markov processes, where some outcome, some effect, is proximately influenced only by a direct primary cause. These are the so-called parent nodes to a given variable, a given node inside a Bayesian network, those that are directly linked. But that cause itself can invariably be traced to some secondary cause, which can be further traced to some tertiary cause and to a quaternary cause, and so on. So the art of causal modeling is to know when to stop, and how much of the detail to omit, especially for the sake of making a decision-aiding tool practical. Here's a real-world example that I've used of polar bear populations that respond to prey availability under climate change. Okay, this can be modeled in a causal web with multiple tiered causality, where the polar bears eat the seals, that eat the fish, that eat the shrimp, that eat the algae, that grow on the underside of sea ice, the suitability of which is influenced by the thickness of the ice, which in turn is a function of how much input of warming and solar insolation there is, which is influenced by climate change. So again, where do we stop? This is part of the practical experience and the art of causal web modeling. And furthermore, each of these levels, each of these nodes are or can be themselves entire causal webs. The whole web can just blow up. All of them can also contain latent variables, hidden variables, confounding variables, lurking variables, things that are very difficult to represent even in a Bayesian context. So my overall point here is that causality and probability itself are nested. They are recursive, and in a sense, they're fractal, in that they occupy partial extents to varying degrees of the entire possible causal space. So here I'm introducing the concept of calculating an index of probability in a causal network as a fractal extent. And yes, that's the simple formula for a recursive fractal there. So this is another face of probability. By the way, too, this is where I drew the line, so to speak, in my Bayesian network analysis of polar bear population response. So let's take a step onward and ask, is probability absolute? This is addressed by the line of thinking, the philosophy, if you will, of Bayesianism. Bayesianism. There are a number of good summaries available on the topic, and I'll be happy to share these with you afterwards if you like. But basically, Bayesianism asserts that knowledge is subject to experience, and additional experience is used to refine or redefine expectations of outcomes. That's the use of updating priors and recalculating the posteriors. So to answer the question, is probability absolute? It logically follows that probability is relative. It's relative to initial knowledge and it's relative to subsequent experience. It is not absolute. The concepts of Bayesianism have been used in many contexts, such as in forensic proof in a court of law, in medical diagnosis, in weather forecasting, and much, much more. So it's a very, very practical approach and concept. David Kay has written on 7 types of probability. I won't go into any of the details here, but note that this epistemology covers the range of concepts from, covers the range of concepts of probability from strictly computational all the way down to individual systems of belief. And David Kay concluded that the law of evidence necessarily involves the use of prior information or beliefs. Again, arguing for the relative nature of probability, especially in real-world contexts, such as in evidence-based court trials or any kind of evidence-based management. So let's take this a final step further. Does probability in some way exist? Is it in some way real? This is addressed by the philosophy called cubism, quantum Bayesianism. But cubism is not to be confused with, well, cubism, which itself, by the way, really nicely depicts reality in a hyperdimensional perspective. But I digress. Back to cubism, which also has a very nice published foundation to it. Adherents of cubism are cubists. No, not cubists, cubists. And the 2 central tenets of cubism are, number 1, that probabilities are artifacts of observational uncertainty, artifacts of uncertainty, observational uncertainty, in fact. This says that ambiguous experiences, uncertainties, can be rectified through direct measurement. This also derives from amplification wave functions from quantum theory. But it seems to make sense inside the Bayesian world too. And the second main tenet of cubism is that probability is subjective knowledge. It's a result of incomplete understanding. So in the cubist view, probability is an effect of that incompleteness. It's an outcome of uncertainty. And it's a result of one's degrees of belief. But, and here's the kicker, probability is not some absolute inherent attribute of real things. What do I mean by that? Well, flipping a fair coin many times results in about a 50-50 split between heads and tails. But 50-50 or 50% is as would be argued by the cubists, are not actual physical attributes of the coin itself. It's even been argued that cubism is essential for rectifying the subjective scientist with the objective world that they study. That it's as much a matter of psychology as it is philosophy and of operant statistics. So a final monition, final caution, be careful here, as the cubist view of probability as being wholly relative can degenerate into what I will call probability solipsism. That is, that all probability is just in your head. Personally, I would not want to test such an assertion as a test subject myself. So this has been a quick trip through at least some of the many faces of probability. I hope you've enjoyed it. Hope you got something out of it. And thanks very much. I'll turn it now back over to our most worthy moderator, Dr. Bengtson. Thanks very much.
Thank you, Bruce. I really appreciated at the start of your talk you taking the time to define words like probability and likelihood and make distinctions there, because I think in our world, it's so important for us to be able to define these words so that when we're having conversations with each other, we're not talking across each other, and we make sure that we're talking about the same concepts and we're on the same page. So I really appreciated that. And thank you for the very interesting and engaging talk. Just a few notices for everyone about some things that are coming up in the life of our society at the Australasian Bayesian Network Modeling Society. We have our annual conference that's happening from the 15th to the 18th of November. That'll be a chance for us to get together virtually and exchange science and connect with each other. It's open to everyone, for people who are interested in Bayesian network modeling and people who work in that space. So please come along. You can find more details about that on our website. We also have another webinar coming up in this series. It's entitled No Data, No Problem, Flexibility of Data Sources in BNs by Dr. Helen Mayfield. So I'm very much looking forward to that. There she is. That'll be on the 6th of October, starting at 12 p.m. for half an hour Australian Eastern Daylight Savings Time. So really looking forward to that. Please come along and tune into that as well. You can also find out more details about us on our website at abnms.org.